Okay, here's example 5 from 4.3. We're going to probably do 2 more videos, this one and then the next one to cover example number 5b. I know that's a lot of little videos, but I thought maybe you'd rather have a lot of little videos than one big old long video. But if you look at our calendar, 4.3 would have probably taken us at least 3 different days in class to do, so that's why it's kind of so long, because there's so much information. So hang in there, guys. So let's look at example number 5a. It says to determine the intervals on which the graph is concave up or concave down. So remember, concavity is determined by our second derivative. So we've got to figure out what our second derivative is, set it equal to 0 or does not exist to find the possible points of inflection, and then do our sign chart to figure out if our second derivative is positive or negative. So here's our function, 6 over x squared plus 3, and we've got to find our second derivative. So before we find our second derivative, we obviously have to find our first derivative. So what derivative rule would you use to find the first derivative on this one? So there's a couple different things you can do. The first thing I noticed maybe was quotient rule, or you could bring up that denominator, call it that quantity to the -1 power, and use chain rule. Either way, we should all get the same final answer. But what I did is I used the quotient rule. So try that, pause your video, try finding the first derivative and see if you get the same answer as me, no matter which rule you use. I did quotient rule. I did the bottom times the derivative of the top. Remember, the derivative of any constant is 0, minus the top times the derivative of the bottom over the bottom squared. So 0 times anything, that part just zeroes out. And so I ended up getting a simplified first derivative of -12x over the quantity x squared plus 3 squared. But that's just my first derivative. If I was asking about increasing and decreasing, we could stop there. But the question is really asking me for concavity, so I need to go down to my second derivative. So now I'm going to use my first derivative that I got over here, and I'm going to find his derivative. So to me, this looks like a quotient rule with a little bit of chain rule in it. So again, pause your video, try to do quotient rule with your chain rule, and see if you get the same answer as I do. Okay, I did the bottom times the derivative of the top, minus the top times the derivative of the bottom, and that's a chain rule. Bringing your 2 forward, keeping your inside the same, and then don't forget to multiply by the derivative of your inside, over the bottom squared. Okay, so that's where I got the blue stuff from. From there, I want to see if I can simplify a little bit. And so it looks like I combine some of my like terms here. I put the -12 in the front, so I have -12 x squared plus 3 squared. Remember, the negative and the -12 made a positive, and so that's where my positive came in. I've got 12 times 2, which is 24, times another 2x, or I should say 12x times 2 times another 2x is my 48x squared, with my x squared plus 3 right there. So that's where that came from. Hopefully that's making sense so far. Over the bottom, which is my quantity squared, then squared again. And remember, when we raise to a power, we really multiply the exponents, and so that's why it turned into a new exponent of a 4. All right, I still want to make this look a little bit nicer, because remember, we're going to try to take this second derivative and set it equal to 0 and does not exist. That's the top equal to 0 and the bottom equal to 0. So we really want to try to get that top to look as nice as possible in a factored form so that we can set each piece equal to 0 instead of a whole bunch of different terms being added or subtracted. So looking at my top here, my numerator, is there something that I can factor out of each term? I notice that I have a term here and a term here, and I want to try to factor. It looks like in each of those terms, I can at least take out a -12, can't we? And also in both of those terms, they both have an x squared plus 3. So I'm going to GCF out a -12 and an x squared plus 3. If I take out a -12 and an x squared plus 3, the -12 goes away on this part, and one of the x squared plus 3's goes away, but I'm still left with one of the x squared plus 3's. So I'm going to leave my leftovers in the parenthesis. Again, I took out a -12, I took out an x squared plus 3, and I have left over an x squared plus 3 still. In my second term, if I took out a -12, if I divided 48 by -12, I'm left with -4. I took out an x squared plus 3, so that part goes away, but I still have the x squared next to my 48 left over. So again, I took out a negative 12, I took out an x squared plus 3, and I have leftovers then of x squared plus 3 minus 4x squared. So now I can make those leftovers look a little bit nicer by combining my like terms. And so I can say that my second derivative, as simplified and factored as possible, would be negative 12 times the quantity x squared plus 3 times the quantity negative 3x squared plus 3 all over that denominator. So now that my second derivative is simplified and factored, we can now figure out our possible points of inflection. Where does our second derivative equal 0 or does not exist? That means I'm going to take the numerator, the top, and set it equal to 0. I'm also going to take the bottom and set it equal to 0, so I can find my possible points of inflection. That's why I wanted to factor the numerator so that I have 3 nice pieces being multiplied together, and if they're set equal to 0, well then that must mean that the first piece equals 0, the second piece equals 0, or that third piece equals 0, and I can set each piece equal to 0. When I set the negative 12 equal to 0, that part kind of doesn't make sense and kind of goes away. When I set my x squared plus 3 equal to 0, if you think about it, if you subtract the 3 from both sides and you try to square root, you're now square rooting a negative number, which are imaginary numbers, and we're not dealing with imaginary numbers on these problems, just the real number system. So that part also kind of goes away. So my second term, if I subtract the 3 and I divide by negative 3, I now have x squared equals 1. I can square root both sides, and be careful, you should end up getting x equals plus or minus 1. So I have possible points of inflection at x equals plus and minus 1, correct? Okay. When I set the bottom equal to 0, I end up having an x squared plus 3 to the 4th power. What that really means is I just have 4 of these. So you could write it out 4 times if you wanted to, and then set each piece equal to 0. Or know that if you just do it once, you're just going to have the same answer 4 times. If I set that piece equal to 0 and I subtract the 3 over and square root, well then again I'm square rooting a negative number, so those end up just being imaginary numbers. So I really only get possible points of inflection at x equals positive and negative 1. Okay? All right, you know what I just thought of? I thought of something real quick that we probably should have looked at the very beginning. If you look at our original problem, doesn't this have a fraction and a denominator? And so that should have been a red flag at the very beginning because we're concerned with that denominator equaling 0. So is there a time that this denominator is going to equal 0 and cause an issue in my domain? Well, if I set it equal to 0 and I tried to solve, I'm going to get those imaginary numbers again. So so it doesn't look like there's any issues in my domain. And so there's no number that's going to cause that denominator to equal 0. There's no holes, there's no vertical asymptotes, so it looks like I'm good. But I probably should have double checked that at the beginning. Okay, so going back here, I still have possible points of inflection at x equals negative and positive 1. So this is where we're going to do our sign chart. Remember, with our second derivative, we need to plug in a number less than negative 1 in our second derivative, a number in between negative 1 and 1, and a number greater than 1 in our second derivative. So going back to your second derivative here, we need to plug in a number less than 1, in between negative 1 and 1, and greater than 1. Okay, so if I plug in a number that is less than negative 1, I don't know, can we say negative 2? If I plug in a negative 2 and I square it, isn't that 4? And 4 plus 3 is 7, is that positive? So I get a positive number right here. My 12 is negative. If I plug in a negative 2 here, negative 2 squared is 4. 4 times negative 3 is negative 12. Negative 12 plus 3 is some sort of negative, right? So I have a negative number times a positive number times a negative number. So doesn't that give me a positive on the top? On the bottom, if I plug in a negative 2 and I square it, that gives me 4. 4 plus 3 is positive. Something positive raised to the 4th power is still positive. So I got a positive divided by a positive. So instead of actually plugging in all the numbers and figuring out what the answer is, I really just care about what the sign is. So positive divided by a positive, to me that's a positive over there in that interval. Do the same thing with the other intervals. Plug in your numbers into your second derivative and see if your answer turns out to be positive or negative so we can figure out our concavity. So pause the video, practice those last two intervals, and let's see if you get the same answer as me. Okay, in the interval from -1 to 1, when I plugged in a number, I tried 0 because that was the easiest. I ended up getting a negative. In the interval greater than 1, I plugged in, 2 into my second derivative, and I ended up getting a positive in my second derivative. So I have positive, negative, positive. This should help us figure out our concavity and if we have any points of inflection. Remember, our function f is concave up when our second derivative is positive. My function f is concave down when my second derivative is negative. So it looks like f is concave up from -infinity to -1, and then again from 1 to infinity. And if I asked you to justify, you can say that you know it's concave up because the second derivative is positive. We also know that it's concave down from -1 to 1 because the second derivative, concave down from -1 to 1, I hope I said that, because the second derivative is negative. And so anytime there's a concavity change, then I know that I have a point of inflection. So it looks like there's a point of inflection at x equals -1 and also at x equals +1. But remember they're points, so we need to write them as points, x, y's. And so in order to find the y value that corresponds to the x value, remember we're going to plug those into our original equation so we can find the point on our original graph where it changes concavity. So I need you to plug in -1 to our very original equation, and I need you to plug in +1 to our very original equation so we can get those points of inflection. I ended up getting points of inflection at -1, 3/2 and at +1, 3/2. So I know where this graph concaves up, concaves down, and any points of inflection, all by using my second derivative. All right, make sure you practice that one. We'll do one more video for example number 5b, and then we'll be finally done with section 4.3. Hang in there, guys.